Big Bang, guys. Welcome to the course Life, Evolution, Universe. And we will start at the beginning, we'll start slow, we'll start at the Big Bang. So, as we know, the universe is expanding, so there has to be a beginning. And we call this the Big Bang, which happened 14 billion years ago. And this is now the prevailing cosmological model for the universe in its earliest known periods and through its large-scale evolution in time. So, this event happened everywhere, and it could be seen as the stretching out of a homogeneous and isotropic universe. So there's no special place. This is very important. And this theory is actually a big change in scientific research, as the universe was first thought to be eternal and static. So the very early universe was super hot and dense and was expanding incredibly quick, so not accepting our current laws of physics. And before any stars had formed, the universe was just a lot of spread out gas and dark matter. So,
But Jan-Pieter,
yeah?
what is dark matter?
That's actually a very good question. So dark matter is matter that doesn't interact with things other than by gravity. And because it's dark, we can see it, we still don't know what it is. So this is still ongoing research. But I'll continue. So as the universe was expanding, its expansion slowed. And when the universe could slow down, things were actually allowed to form. So gravity would cause slightly denser areas of dark matter to contract into clumps. These contracted clumps would start to rotate, causing the forerunners of our galaxies. And when gravitational attraction caused the clumps to compress sufficiently, they were actually allowed to start thermonuclear fusion. And in this way, stars were formed. And clusters of stars could merge together, forming galaxies as we see them today. And I think we probably all know the galaxy where we can find ourselves, right, Juul?
The Milky Way?
Indeed, Juul, the Milky Way. So in these galaxies, we also see planets. And this is something where Anke will tell you more about in the next class.
Okay, last lecture, Jan-Pieter taught you about planets, but not all planets contain life. And I'm here to tell you why Earth contains life and other planets do not. To start with the simple one, the Earth has a circular orbit, which means that it's never too close to the Sun, that it will heat up too much, or too far away from the Sun, that it will freeze over, and that there is no life available on Earth. If Earth were 5% closer to the Sun, all the water in the oceans would evaporate and there would be no life. But if Earth was 5% more far away from the Sun, all the oceans would freeze over and it would be way too cold to support life as well. Now, I kicked it off. Does anybody else have a suggestion about what we need for life on Earth?
The magnetic field, maybe?
Indeed, Juul. The magnetic field is very important to Earth's existence as we have it right now, seen as it protects us from the damaging radiation from outer space. We also have another protective layer called the ozone layer, which protects us from UV lighting, which can be detrimental to us as well, and also keeps the atmospheric composition as it is right now, which Cole will tell you about later on. We also have the Earth's gravity, which is just the right amount of force for us to not succumb to the effect, and also have hydrogen in the atmosphere. So let's write that down as well. And the actual tilt of the Earth is also very important for good temperature distribution, and it will not get too cold and too hot in the same places because of this. So these are all very important factors to life on Earth as we know it right now. And these are also some of the things we look for when we try and search for other planets with life on it. This is still a field of ongoing research as well, to try and find more of these characteristics. We'll try and look for further out for the places where we can find life.
Good morning, class. I'm happy we're all present on this early Friday morning. There's probably an accident today. Today we'll talk about the Great Oxygenation Event. The early Earth had a reducing atmosphere. This atmosphere did not contain free oxygen.
Yeah?
But if there's no oxygen before, how come there's oxygen in the atmosphere now?
Nowadays, the surface of the Earth is largely oxidized. The change in the concentration of oxygen in the atmosphere took place 2.4 billion years ago. And yeah, when did this take place?
Early Proterozoic era?
Yeah, very well. So this event is called the Great Oxygenation Event, and this has set the stage for complex life. Oxygen would eventually achieve concentrations able to support large and multicellular life of organisms. The cause of the Great Oxygenation Event is still hotly debated, and I will discuss two hypotheses with you. The first one is the oxygenic photosynthesis. The origin of oxygenic photosynthesis led to the production of oxygen and therefore the oxygenation of the atmosphere.
Well, isn't that enough evidence already?
No, the problem is that there is no evidence for this. Oxygen cannot build up in the atmosphere since oxygen is consumed by many processes such as respiration and spontaneous oxidation. The second hypothesis is hydrogen escape. Due to hydrogen loss to space, there is a permanent oxidation of the Earth's surface. But the problem here as well is that there is no evidence for this. We can conclude that there's still a lot to discover, and therefore it is important to be comfortable with not knowing the answers to everything. The Great Oxygenation Event is a representation of the co-evolution of Earth and life. Earth and life co-evolved and they transformed each other in building the biosphere of today. There is a continuing interplay between genetic possibility and ecological opportunity. So this was all you have to know for the exam of next week. Good luck. Are there any questions?
Will the test be multiple choice?
No multiple choices. We do it hardcore.